Hi everybody, it's Mrs. Walsh and this is our lesson on deductive reasoning. So our objectives for this lesson is to learn about the law of detachment and the law of syllogism and use them to determine the validity of given statements and also use them to write a valid conclusion. So I told you before, I really love logic and this gets into some of the interesting parts of logic. All right, so the two different types of reasoning that we tend to discuss are inductive reasoning and deductive reasoning. Inductive reasoning is based on patterns you observe. So I don't know if you've ever heard people use the word, I induced. I mean, it's basically a conjecture. The conjectures you reach are conclusions by inductive reasoning. For example, if you just saw the pattern 5, 10, 20, 40, and you were asked to find the next three terms, you would say, that you would notice these are all doubling. So you know by inductive reasoning, based on the patterns you observe, that this would go to 80, 160, etc. All right, but what we tend to do a little bit more in geometry is look at deductive reasoning. And it's sometimes called logical reasoning. It's the process of reasoning logically from given statements or facts to getting to a conclusion. So you guys are going to become very familiar with proofs, and proofs use deductive reasoning, where you reason logically from one statement to the next to reach the conclusion you're trying to prove. So here's one of those phrases that you've got to learn, you've got to memorize, and it's important, and it's called the law of detachment, and it's pretty straightforward. It's basically saying that if the hypothesis of a true conditional is true, then the conclusion is also true, and you're going to see why this makes sense. So symbolically what that means is, you notice here's our conditional that we're used to showing. If P then Q is true. So if this is a valid, I don't know why it keeps doing this. Let me try to get rid of these. Okay. If P then Q is true, if it's a valid conditional statement, and I'm telling you that P is true, and I've told you if P happens, then Q always happens, then if I tell you P is true, guess what? Q is true. We know that. So let me show you. It's always easier to look at a real example to understand what this means. And this is just called the law of detachment. So basically, if I'm telling you that if a student gets an A on a final exam, then the student will pass the course. That's my conditional. If P, a student gets an A on final exam, then Q, they will pass the course. That's my true conditional. And here I'm telling you that Felicia got an A on her history final exam. So I'm telling you P is true. It happened. She got it. Well, if P is true, then Q is going to be true, right? Because that's what the law of detachment tells us. So then we know that in fact, come on. The second statement matches the hypothesis of the conditional. This statement matched P. So by the law of detachment, I know that it's the valid conclusion, and basically Felicia will get an A on her history Felicia will pass the course. And it's written down here, but our valid conclusion is that Felicia will pass the course. Because I knew if P then Q was a valid statement, I told you P happened, Q's got to happen. Okay, here's another example using the law of detachment. What can we conclude using the law of detachment from the given true statements? First, I'm giving the conditional. If P, a ray divides an angle into two congruent angles, then Q, the ray is an angle bisector. So I know if a ray divides an angle into two congruent angles, then that ray is an angle bisector. Now, I am being told that this ray, RS, divides this angle so that they're congruent. So I'm being told that P happened. Look, it happened. A ray divided the angle into two congruent angles. So if I know P is true, and P then Q was a valid statement, now I know Q is going to be true. Therefore, this ray has to be an angle bisector. So if we look at it, you can see here that the second statement matches the hypothesis of the conditional by the law of detachment. So therefore, the valid conclusion there is that the ray is an angle bisector, or specifically, RS bisects angle ARB. All right. Now, what about this one? What can you conclude from this? If two angles are adjacent, so here's my P, this is my hypothesis, then they share a common vertex. Here's my Q, here's my conclusion. Well, I'm telling you 1 and 2 share a common vertex. Now, if you will recall, the law of detachment tells us first you've got to have a valid if P then Q. Then you've got to prove that P is true. Well, what is this? 1 and 2 is Q. It's the conclusion. It's not the hypothesis. So just because you tell me 1 and 2 share a common vertex, the law of detachment does not tell me, I can't use the law of detachment. I can only use it when I'm given a conditional and then I'm told the hypothesis part of the conditional is true, not the conclusion part. And logic would tell us that's true because I could have an angle 1 here and an angle 2 here, and they share a common vertex, but they're not adjacent. So, therefore, in this case, the second statement doesn't match the hypothesis of the conditional. It matches the conclusion of the conditional. So I can't make a conclusion based on the law of detachment. All right, what about this? If there's lightning, that's my hypothesis, then it's not safe to be in the open. That's my conclusion. And now I'm being told that Marla sees lightning from the soccer field. So my P has happened. Therefore, I can definitely conclude by the law of detachment that Q, the second statement, matches the hypothesis of the conditional, and therefore it is not safe to be on the soccer field. I can now say Q is true. All right, so that was the law of detachment. Basically, if P then Q is a valid conditional statement, we prove that P is true, then we know that Q is going to be true. If we prove the hypothesis is true, then we're definitely getting to that conclusion. Now, let's look at the law of syllogism. This allows you to state a conclusion from 2 conditional statements when the conclusion of one statement is the same as the hypothesis of the next statement. And as we go through this, I want you to think about whether this reminds you of a property that you've learned in math and in algebra. And we'll talk about that tomorrow. But let's look at this symbolically. What we're saying is if we know P then Q is true, and Q then R is true, then we say, well, if P and Q is true and Q then R is true, is guess what, guys? We can skip that middle step and we can go straight to saying if P is true, then R is true. Hint, hint, does that remind you of anything? All right, so let's look again. Another way of looking at it symbolically. If P then Q is true, and Q then R is true, and maybe this helps you see it better because you can just kind of cross them out, then it leads us straight from P to R. We don't have to take the Q step. All right, so let's look at an example. What can you conclude from the given true statements? If a figure is a square, here's my hypothesis, then the figure is a rectangle. The conclusion is the figure is a rectangle. Now look here. I'm using that same conclusion. If the figure is a rectangle, then the figure has 4 sides. That's my new conclusion. So what this allows me to do in a kind of transitive way is if a figure is a square and the figure is a rectangle, and, well, by the way, if the figure is a rectangle, then the figure has 4 sides, I'm allowed to leap directly to saying, since these two match, I can go directly from saying that if the figure is a square, then the figure has 4 sides. I don't need the middle part. And it works. And all this is doing, writing down there, is what I said. If a figure is a square, then it has 4 sides. I don't need to twice repeat figure's a square, then it's a rectangle, figure's a rectangle, then it's a square. I can directly, from a transitive perspective, go straight from P to R. Okay, let's look at this again. What can you conclude from the given true statements? If you do gymnastics, here's my hypothesis, then you are flexible. Here's my conclusion. If you do ballet, this looks like a whole other statement. I'll call it R. Then you are flexible. That's back to my other conclusion. Well, if you'll recall, the law of syllogism is P then Q, Q then R, P then R. This isn't doing that. This is going P then Q, R then Q. It doesn't work. It's not the law of syllogism. So you can see, and they'll be color-coded here, that the ones that match are supposed to be this one, and they don't. It's these two that match. The statements have the same conclusion, but neither conclusion is the hypothesis of the other statement. Therefore, we cannot make a valid conclusion from this information. Okay, how about this one? What can you conclude from the given true statements? If you live in Accra, here's our first hypothesis, then you live in Ghana. Here's the conclusion I can make. If you live in Ghana, let me get some highlighted colors here. You can see that one matches, right? Then you live in Africa. Here's another conclusion. I'm being told that Asia lives in Accra, so I'm being told P is true. So I'm kind of combining two things here. If you remember the law of detachment, it tells me that if I have a valid P then Q, and I'm being told P is true, then I know Q is true. Well, I can create a new P then Q from this. I can say, if you live in Accra, I can go straight to the conclusion that you live in Africa. I don't need the interim step of Ghana. And now that I'm being told using the law of detachment that in fact Asia does live in Accra, then I can make the logical conclusion that if Asia lives in Accra, that she in fact does also live in Africa. I don't know why it's going so slow, everybody. I'm sorry. So now, using the third statement, I can make the final conclusion that Asia does in fact live in Africa. All right. So that's it for this lesson. Make sure you're ready for a quick quiz tomorrow. Be very comfortable with the law of detachment and the law of syllogism, and I'll see you tomorrow.